so we already had this covered in theory, and we also did the precipitation task where we also spoke about, sorry, let me just check, my enter is not working. So it doesn't want to go forward. All right, now here we are. So where we already discussed a little bit the crystallization as well. And what we pointed out, that the crystallization is actually a precipitation that results in formation of crystals. And unlike the precipitase, crystals have a very defined structure. And even though the process is very similar, crystallization needs to be done more slowly and under better controlled conditions in order to achieve such structure. Now we can achieve the crystallization in several ways. And one of them is the change in the temperature, or the reduction of the temperature in the system, but it can also be done by evaporation, sublimation, addition of anti-solvent, etc. But let's have a look here first into our solid liquid phase diagram. Just a second, so I open the pointer. All right, you should now see my red dot. All right, this is our solid liquid equilibrium diagram. And it shows us the composition of the system with the change in temperature. And here, as an example, we have water and protein system and their solid liquid equilibrium diagram. So in this area, which is in white, we have a solution, which is a protein water solution. So first, let me here describe the most important terminology, and then in the next slide we will see how we read the diagram. So here we have a liquid, which is our protein solution. In these sides, so when we come to here, this is our liquidus line. Below the liquidus line, here what is marked in blue, and here what is marked in red, we have our protein solution as well as the crystals. If we would to begin somewhere here, we would end up, if our initial composition of the solution was somewhere here, we would end up, and we lower the temperature, we would have our solution and protein crystals when we would cool down the temperature. Or if we would have our initial composition somewhere here on the left side, we would have, since we have water, we would have ice and solution. If we continue to cool down our system, we would reach a eutectic point. Has anybody heard before about such diagrams, and do you know what eutectic point is? Is in general crystallization in solid liquid equilibria familiar to you? Yes? No? It's difficult when it's over the Zoom. I don't see anybody, and I don't know what you are thinking. Sadly not. All right. What is important to know is the areas of the diagram. So you should know that here we are we have a liquid. These two lines are called the liquidus lines, and they mark the area where so when we decrease the temperature, when we start going from one phase region, which is our liquid, to a two-phase region where we have a solid and a liquid. Now, solid liquid equilibriums also have a point which is called a eutectic point, where so if we would, let's say, be on this side, we come to the liquidus line. Then first we would have a solution of this composition defined by the liquidus line, and we would have pure ice or pure water crystals. As we would lower the temperature and crystallization would take place, the solution concentration would move along the equilibrium, so the liquidus line. And once we reach the eutectic point, we start having also the crystals of the second component. So then we would start to also have the crystals of our protein. And this point, the eutectic point, is a point when both of our components start to participate at this composition that we would read at the bottom. Now, in crystallization, we also have this metastable zone, which is the zone around, so right below our liquidus line. And in this zone, even though we have reached the supersaturation, we do not yet have enough energy in our system to form the crystals. So in this area, the interfacial energy, or the interfacial energy, is opposing the driving volume-free energy, and our crystals cannot nucleate. But we can achieve the nucleation if we add, so if we skip, we can skip this nucleation by, or not skip, we can help the nucleation if we add crystals of the same type or of another type, which will help the crystal growth. And this is why this area is called the metastable area, because we cannot have spontaneous growth of our crystals. So this is what I was talking about. Here we have liquid, before it was the protein solution. Here we have solid and pure liquid 1. And here we have liquid and pure solid 2. And as I said, we can achieve this by changing the temperature. So yes, this is what you should know about these diagrams. Now, maybe I don't have here an example, but you should also know that this diagram does not have to be straight here, but can look somehow like this. So we can have this situation at both of our ends. This means that instead of having pure crystals, we would be having our liquidus on this side and mixed crystals on this side. So this means that by such precipitation, or when we have phases which behave in such a way, we cannot achieve pure crystals of one kind. Erase what I wrote. Right, I hope it doesn't stay. Somebody has the question? James?
Yeah, I have a question. I've always seen this kind of graphs, but I've never seen them draw with the metastable area. So I just wanted to ask, I can imagine that it is always present, but I've always heard about adding acid to enhance the forming of crystals, as you already mentioned. So is this only made on that area, or is it always made?
Yeah, so only in this, normally this metastable area, we know it exists, but it's not normally drawn, as you see in these diagrams. It's not always drawn in such diagrams. But it's just for your information, so you know it exists. And what is characterized, yes, that you don't have, so you do have oversaturation of your solution. But yeah, crystals, in order to initiate this, the formation of the crystal structure, you need some energy, which is not enough. And yes, in this case, we would add some crystals, as I mentioned, of the same type or of a different species to help the crystallization. Does this answer your question?
Yes, thank you.
Okay, you're welcome. All right, anybody else? I don't have an overview of all I have a question. Can you please record the session? Now it's a bit late because we've already started, but if somebody couldn't make it, or if you have any questions, we can schedule an appointment and organize the consultation. So I will repeat this for you, or if something is unclear. I mean, the rest of the exercises were in person and also not recorded. So I'm not sure why the request, but yeah, this time I'm not recording, since anyway the rest of the exercises are not recorded. Okay, more questions about this? All right, good. Now when it comes to reading, such diagrams, it's pretty straightforward, and you can apply the lever rule the same as we've done before with ATPS, for example. So if we have our beginning composition here, for example, at F, and we start to cool our solution, and we continue to go down with our temperature, as I mentioned, the composition of our solution, so the liquid composition, is going to change according to our liquidus line, and it's going to have this composition, while in this case we are going to have pure crystals of the species on this left-hand side. And we can determine the ratios of the phases, the masses of the phases, by a simple lever rule. Yes, I will not be repeating it because yes, we've done this, but the principle is the same. So the mass of the liquid phase is going to be proportional to the length of this line over the length of the whole tie line, while the mass of our crystal phase is going to be proportional to the mass to the length of this section of the tie line over the whole tie line. So the principle is the same, and we would be reading the composition here at the bottom. All right. Now, what we have is in our exercise is a protease inhibitor. So an enzyme that we need to crystallize from a concentrated solution. And in this case, we skip this nucleation step by adding a small crystals of the solute to the solution with an initial loading of 0.01 kilogram crystals per kilogram solvent. And we need to double the size or the weight of these crystals before we can remove them from the solution and take them as our product. We have 100 kilograms of solution coming in to our reactor system per hour with a loading of 0.03 kilograms solid per kilograms of solvent. And we are carrying out the crystallization in 2 batch reactors, which are filled alternately. So one after the other. So one, yeah. Maybe take a minute or two to read the task and take a look at all the formulas. And then we will start to solve the task together. All right. We can slowly continue. So what we have is our main equation. What you see, equation 2, which is a differential equation, which describes the kinetics of crystal growth. Of course, you have delta C, which is concentration difference, which is a driving force for this process. And so we have the concentration difference between the actual concentration and the maximum so the saturation concentration, which is basically the solubility. If we reach the solubility, of course, then we won't be having crystals anymore. Then you have the equation 3, which is the crystal's growth rate, and it will depend on your system. M is the exponent. In this case, is 2, but it doesn't have to be. Pay attention to this if this comes in an exam. And we also have 2 equations under 4, which are basically bound to it's a specific area and the specific volume of the crystals. And this is done by, of course, not very realistic, but an assumption that our crystals are spheres or some form close to a sphere. All right. So under task 1, we need to find the relationship between the change in specific crystal surface area and the corresponding change in crystal mass. So if you see here in equation 2, in the differential equation that we will be using later, we have this AC, which is the specific, total specific crystal surface area. So because in our task it is said that our goal is for our crystals to double their mass, we need to find the relationship between the crystal mass and the specific crystal surface area. Just a tip. So we start from these 2 equations that connect the crystal size, so area and volume, and through RC, so the radius of the hypothetical spherical crystal, we can relate these 2 equations and try to connect them to the mass of the crystal. And this AC is, take care that it's a specific, so it's a area of the crystals per kilogram of the solvent as well for the volume. It's a specific volume. All right, I will give you a few minutes and then we start together with the task. All right. Did you guys manage to get a relationship between the specific crystal area and the mass of the crystals? Maybe I give you 2 more minutes and maybe a small hint. The mass of crystals is related also with the crystal volume through the density. It might help. All right. Let's start this slowly together. All right. So as I said, we can relate the crystal volume and the crystal area over the radius of our hypothetically spherical crystals. And from there, we can express the crystal area. So as I said, we can say the volume of the crystals is equal to the mass of the crystals over the density of the crystals. Now, this just takes some rearrangement of the equations, and you need to also take care about the exponents, but this is what you should get. So we can relate the area of the crystals to the volume of the crystals, and we are left with this part, which is basically a constant. And as I mentioned, our volume of our crystal volume is equal the mass of the crystal over its density. Sorry guys if I'm waiting or it's a bit slow. Somehow I'm not getting on time what I'm trying to, because when I click enter, a new row should appear and somehow it does not. All right. Now we know that this A, so the surface of the crystals, if we divide it by the mass of solvent, we will have the specific crystal surface area, which is what in the end we need to bring in a relationship to the mass of the crystals, because it configures in our also equation. Now, if we just simply divide, we need the relationship. If you have a look at the test number 2, you have an equation for the average crystal surface area, and you have the specific crystal surface area at the end over the specific crystal surface area at C0, so at the beginning. And this is basically the ratio that we should get so we can use it in this equation and we can solve the task. Now, once we have this, this is more or less all we need. Now we just need to relate the end to the initial one, and we proceed to have, now this part becomes mass of the crystals at the end over the mass of the crystals at the beginning, time their density. The density of our material is the same, to the power of 2/3. Mass of the solvent, it's simply coming from here. And this is simply this constant. it does not change. And and since all this is the same, and also the densities are the same, what we are left with is m end over m initial. So are the specific crystal size at the end over the specific crystal surface area at the beginning equals mass of the crystals at the end over the mass of the crystals at the beginning to the power of 2/3. I see I have a question in direct messages about something. I think it's related more to the diagram and to the first part. Maybe we address all these questions then at the end of the exercise. We can stay in the session a little bit longer, and then you can maybe ask and we discuss if something is not clear. Is there something in particular to this slide that you have a question about?
Yes, ma'am. I have one question. The area of the hypothetical spherical crystal, we have said that it is equal to the area divided by the mass solvent. How is this? Can you please explain?
No, this is because this is the specific surface area, and this is how it's normally done in literature and used in these empirical equations, that we have the total area divided by the mass of solvent. And this is why we have it here. This is how in this form it configures in the equation. All right. More questions to this line? All right. Now, once we have this, under our second task is to calculate the time that we need for the crystals to double their weight, and to simplify, because to do this, we need to integrate equation number 2. Now, to simplify, instead of using individual specific surface area, we say that our specific surface area, we take an average value, and it is given by an equation, as you can see right next to the question number 2. Now, try to derive or to integrate the equation number 2 and try to calculate the time on your own. And then in 5 minutes, we try to do it together. I have a question. If somebody wants to know if there is a book with the exercise task that I can recommend, and if so you guys can practice at home as well. Unfortunately, there is not a dedicated book with the exercises example that I'm aware of. I can have a look and see if there are some books that have more calculating examples, but in general, most of the literature is theoretical. Always have a good look into the literature that I believe you can also find in the slides of Professor Gorikov. And yeah, maybe some literature research or some paper could help you as additional examples to how crystallization or how any of the problems that we're doing in these classes can be solved. And if I find an example with the calculating tasks, I will let you know, but unfortunately not to my knowledge currently. Yes, you also say that you found a book that is very good for theory, but not for exercising. Most of them are very theoretical, yeah, unfortunately, with no calculating examples. Guys, if you are writing, maybe to me, write to everyone so people can see what you're writing, because I see this is a direct message as well. The book that this person recommends is the Bioprocess Engineering Principles by Coco Kirja. I believe this one is also listed in the literature, either in the PBL script or by a professor. But yes, there is useful literature and some books that you can as well find in the library. It's very accessible, but as I said, everything is very much theoretical, which is still good and of course will help you towards solving the task. But to my knowledge, I don't know if there is anything that will help you really exercise the calculation part. But I believe if you understand, there should not be any problems coming from the mathematics, so to say, itself. It's all about the logic. But my advice is to study this and to understand what we are doing. All right, did you calculate the average crystal surface area? Okay, this is fairly simple, so we'll just share. We should calculate, so the initial specific surface area is, I believe, given. Yes, it's given at the bottom of the page. And if we calculate the end specific surface area, we just substitute to the equation that we just derived. We get that AC0 times mass n over mass 0 to the power of 2/3, and we should get 0.0865 meters squared per kilogram. Of course, our crystals have grown and our area has increased. Now from this, we can also calculate the mean surface area by simply substituting. You should get 0.0693 meters squared per kilogram. Are you getting the correct values with me? All right, I hope so. Yes, this is also important. The J can be, from equation 2, can be neglected because it's a constant that describes the nucleation step, and we are skipping it in this case since we are adding crystals to help the nucleation or to help the crystal growth. We are not letting the crystals nucleate by themselves. Now, if we go further, so we have that Rj equals to 0. This is the equation 2 that you have that describes the growth of the crystals. This is the average crystal area, and this is our R, which is the overall growth rate of crystals. Now, when we simplify that and when we put the numbers, we get 0.0693, which is our average mean surface area. times 0.1, which is our constant, times delta C, which is the concentration difference or our driving force, to the power of 2, which is the m. This is the exponent. I just want to mention in advance that this m, or this overall growth rate constant, does not always have to have the exponent 2. So when you're studying and you want to prepare for exam, try to solve the integral and to practice your math when this is not 2. Your integral would look different. Now, if we want to solve this differential equation.
Sorry, can you repeat what you just said?
Yes. This delta C squared does not have to be squared. This number 2, this exponent on top, is given. So this is this whole part. So this whole part, sorry, it's not. This whole part this is from the equation 2. The equation 2, and this is your R. So your it's called overall growth rate of crystals. And it's given by the task that for this system, m is 2, but it doesn't have to be 2. It can be 1, it can be 2.5, it can be 3. So take care. When you want to solve this equation, so equation 2, try to solve the integral with different exponents. So you need to know, it's expected of you to know how to solve an integral in the exam. You won't be having complex integrals, but something like this will
Okay,
in a crystallization task. All right, let me just delete what I just wrote. All right, now we've come to our integral. So we need to solve our differential equation, and we do this by doing an integral over delta C on our left-hand side or on one side, and integraling over time, because we had dc over dt, right? So we have these two parts. Of course, we need to go from the initial. So the concentration difference is our driving force, and it's our variable in this case. So this delta C and delta T. So we integral here from delta C initial concentration difference to delta C at the end, and from 0 to R time T, which we need to calculate. Now, in this case, the integral, when we solve it for T and delta C, you will get this. Now, this is why I said, if here wasn't a 2, this would look different. So just keep this in mind. All right. Did somebody maybe already get to calculate the time or bring this a bit forward? All right, just a small hint. So the concentration difference at the time 0, you more or less have, and given everything that it's in the task, you also have the formula. So it's concentration at some time. We know what is the concentration of our solution that is coming into our system. We have this given. What we need to calculate is the delta C after our crystals have doubled their weight. So after we would have achieved what we what the task asks us to. This delta C we can calculate from the material balance for our enzyme, which is crystallizing. So the mass of the crystals, so this is not the concentration is the solute loading. So it's the mass of the solute, the mass of the solute or the mass of the crystals per mass of the solvent. This is why we're multiplying it by the mass of the solvent to be left only with the mass of the crystals. So we have on the left-hand side, at the beginning of our process, we have the concentration of our enzyme, which is in the initial solution, plus the concentration of the crystals at time 0. Yeah, this is what I believe we have. Yeah, it is given. We have 0.01 kilogram crystals per kilogram solvent that we added to start the nucleation. After after some time has passed and our crystals we want to finish our process, we say we want our crystals to double their weight. That's why we have C, which is the concentration of our solute of our enzyme that is left in the solution, plus 2 times mass concentration of the crystal 0. Why we can write here 2 times? Because this is mass crystals or mass crystals per mass of the solution. So we know that the mass of the crystals simply doubled. From here, now you have everything. Of course, when this is an equation, this is the same, this will go out. And the delta C, you can calculate or derive from here. And delta C0, you already have everything given in the task. Now take 2 minutes and then we see what you should get. Did somebody maybe already calculate the time? Because now if you calculate the delta C and you know how to determine the delta C, you can already know how much time we need for the crystals to double their weight. Do you already have
5.3 hours?
Yes, that's true. Let's see now how she got this value. As soon as my computer, yeah, okay. All right, so delta C0, we already said this is the initial concentration of our solute minus the saturation concentration. And you should get 0.015 kilograms of solute per kilogram of solvent. Yes, and as I said, the concentration difference is our driving force. Once our concentration falls below the saturation concentration, our enzyme is simply going to be soluble and we won't be having any crystallization from the solution. That is why we have to be below, and our delta C is the driving force. So as we see, we have our concentration is larger, and this is the maximum, or the delta C 0 is equal to the difference between these two. Our delta C is the concentration at some time t. So this C here at the end of our process minus the saturation concentration. And from this, if you express the C, we can say it's the concentration of our enzyme in the solution at the beginning minus the concentration, or not the concentration, the loading of our crystals at the time 0 minus the saturation concentration. And you should get that the delta C equals to 0.005 kilograms per kilogram. Of course, after some time has passed, we have the reduction of concentration of the enzyme in the solution, and therefore delta C is decreasing. And you now just need to put that into this equation that we derive for T, and you should get that T equals 5.34 hours. All right. Okay. Now under 3, this is the last task in crystallization that we need to do for today. So what is the minimum volume of reactors if the initial density of the solution is 1015 kilograms per meter cube? Now, what is important here to know is that I believe you can easily calculate the minimum volume of the reactor. You already have the throughputs and you have the density. What is important to note is that to calculate the volume of our reactors, we are taking the solution volume, throughput, and the density, because normally the crystals that are forming are denser and heavier. So normally our crystals are going to fall to the bottom of our tank, right? And they're denser than the solution and therefore have a smaller volume. So the maximum volume that you're required, that your reactor requires, is based on the volume of the solution. And this is why in crystallization, normally we take as the maximum reactor demand the volume of our initial solution, because from there, as the crystallization is taking place, it can only go down the volume. All right, try to play with the numbers yourself, a minute or two, and then we share and see what is the volume of reactors. Let me know when you get the reactor volume. All right. Did anybody get the volume? Not yet? Let's do it together so we can go on to our next task for today. So the hourly production of the solution, we know we have, so this is given in the task. So we have, it says 100 kilograms of solute are produced per hour with a loading of 0.03 kilograms solute per kilograms of solvent. And if we know how much solute we have per hour and we know its concentration, then we can calculate the flow rate of the solvent. And with that, you should get 3,333 kilograms per hour. Now we know how long we do our process because we've just calculated that under 2. And we know that we have in total 17,800 kilograms of the solvent. And simply now, when we know the density of the solution, volume equals mass over density, you should get 17.54. Yeah, somebody also here reports the correct value. That's true. 17.54 meter cubic. All right, somebody has questions regarding the crystallization? Because this is the last task in crystallization. We will go on now with adsorption.
Hello, can you hear me?
Yes.
Yeah, so I have a question regarding the first calculation.
First, you mean task 1.0? So
No, here in the task
here.
3.
Yeah.
When you're calculating the feed, we have a loading of 0.03 kilograms of solute per solvent. And then you calculate how much solvent we have, which is 3,333. Then wouldn't you have to add these to the mass of the solute? Because that would be only the solvent that you calculated.
Well, in theory, yes, you can also add the solute, but if you see that these 3,000 something is a lot larger than the mass of the solute, it's not added. But of course, if you have the mass of solute and the mass of the solvent, then it's not wrong to add it. But is it the per mass of solvent or the mass of solution? Because this is this is an important question.
Yeah, exactly. I think it's for solvent.
You should always, you should take care of what is given, but also it is when you have such a big difference, it's also justifiable to approximate. So both would be an okay approach.
Yeah, okay, thanks.
You're welcome. Okay, more questions to this calculation or to crystallization?
Yeah. How common is that we ignore the value of the J value? I forgot the name.
The concentration of the solute?
No. Let me check.
J.
Yeah.
All right. It's common.
Right. Yeah.
It's common. What he is referring to, the J from equation 2 for somebody who didn't maybe follow. It's common. So usually we, when you do a crystallization, you're working in a metastable area where you don't have a spontaneous nucleation, but you try to have a more controlled nucleation by adding some pre-existing crystals that will help the nucleation. So it's very common that you skip this nucleation step and that this J is 0. But of course, in case a task comes up and it's not 0, it's just going to be a constant value and it will be, of course, given. All right.
Okay, thank you.
And the trick to know if we can disregard that is the seed crystals.
Yes. So we would, exactly. So if you add seed crystals, means you don't have a spontaneous nucleation.
Yeah,
okay. More questions to crystallization? Okay. then let me close the crystallization presentation and let's go on to adsorption. I will stop sharing for a minute. You see the adsorption presentation, right?
Yes.
Okay, perfect. So in adsorption, what we have is basically we have a solute. Let me just take my pen. We have our solid compound, which is in some solution, bulk solution. And what we do, we add an adsorbent material on which our solute is going to bound to. And then if it's bound to our adsorbent, then we call it an adsorbate. And the solute adsorbs at the adsorbent until the equilibrium is reached. So we do an adsorption process at its equilibrium conditions, and we describe this equilibrium by an adsorption isotherms, to which I will come in a bit. Now, similarly, as we also had in for example, extraction, when we have an adsorber, we can specify this is our inlet, where we have solution of a certain volume, and we have a concentration of our solute in this solution. What we end up with is, again, a solution with some different smaller concentration of our solute in this solution. This is our adsorbent, so our material onto which we adsorb. This is the loading. So since this is a solid phase, we cannot describe it as a concentration, but we define the amount of substance on an adsorbent by using loading, which represents the kilogram of our solute per kilogram of adsorbent. And of course, after the equilibrium conditions are reached, we again have our adsorbent with some new larger loading of our solute species. And from this, we can simply create a mass balance. So of course, inlet in the solution plus inlet on the adsorbate equals outlet in the solution. This is the mass of the target compound plus the mass of the target compound that has been absorbed. And from this, we can derive our operating line, which takes this form. Now, there are many adsorption isotherms, and as I said, the adsorption isotherms describe the equilibrium loading or the equilibrium relationship between the loading and the concentration of the solute in your solution at a constant temperature. And there, as I said, there are many approaches that we can use to calculate. The two that we will be mentioning here are Freundlich, which predicts an exponential dependency and is also meant for a multi-layer adsorption, and Langmuir, which is mainly which assumes the monolayer, so only one layer of adsorbent forming on our adsorbate. But of course, there are others such as linear, BET, etc. But these two models we will be using in our class today as an example. Now, as I said, all these adsorption isotherms so they have different forms, these equations, but they all, so yeah, they are derived differently, but they all always connect two things, which is the concentration, the equilibrium concentration of our solute in the solution and the loading on our adsorbate. Of our adsorbate on an adsorbent. Normally, practically, how we determine these isotherms and these concentrations is experimentally by simply bringing our solution with a known concentration of our target compound and a known mass or known quantity of our adsorbate. We bring them into contact, so we have our solution, and we also add our adsorbate. We keep them at the constant condition, so these isotherms are always given at constant temperature and pressure. We keep them for a long time. Here as an example is given 72 hours, but we need to give them long time to equilibrate. Then we separate the solid from the liquid phase, for example, by centrifugation. And then we measure the concentration of our target compound in the liquid phase. We can do this by example by using the chromatography, or in this case as an example is given the supercritical fluid chromatography. And this is how we know how much of our target compound we began with and how much we ended up with. And we can also know then how much has been absorbed and determine the equilibrium line for so our absorption isotherm. In practice, this is how it looks. I'm sorry, this is a mistake. This should be not grams per liter, but per mass of adsorbent. I will correct this when I publish this presentation for you, but just so you know. So our loading is always given as a mass per mass, and the concentration is normally given as a mass per volume of the solution. Anyway, to get back, what I wanted to show you by this is that when you have an adsorption process, to determine the end, so if to know what is going to be the end concentration of our solute in the solution and what is going to be the end loading of our target compound on the adsorbent, we do this by simply plotting the adsorption isotherm versus the operating line from the equation that I previously showed you. And this meeting point represents the final loading and the concentration that we will have after our equilibrium has been reached. Now, in our adsorption task, maybe take 2-3 minutes to read, and then we start to solve the tasks together. And just a small tip, maybe, so you, for this adsorption task, you can either do it by pen and paper. You have in this task, the diagrams are given in the PDF that I uploaded. And you can use it as a guidelines for maybe what to do. And also maybe what is easier and much faster for you is if you directly use Excel, since all of you are already on your computers. Maybe Excel would be faster because we will need to plot these diagrams. Yeah, so I give you 2-3 minutes to read the task, and who is ready, you can already start solving, and then I'll follow up and start solving it together with you. I have a question in the chat from where we can take the data to make a graph. It's given in the sheet that is uploaded to StudIP for batch absorption. You're welcome. So the data is basically here now on the screen, and this is the same that you have in your sheets. So normally, in order to solve analytically the task of absorption and to work with absorption isotherms, you need to also determine the empirical constants that configure in these equations. And to do that, the easiest way is to linearize them and to plot them in a linearized form, because then we can or these constants by the slope and the cutout of our diagrams. So to solve this task, I advise you to first linearize the isotherms mathematically, so on with pen and paper, and then to plot the data in a linearized form. You should check which of the isotherms fits the given data the best. So if you're plotting in Excel, if you're working with Excel, that would be the most straightforward way for you, because then you can just fit the line and see what which adsorbent and which model also fits better. And you can directly read the epsilon axis and determine the slope from these diagrams. Try to linearize the equations and try to get the values that are so you have also on this page, you have a page 2 on your sheets, and that will also guide you and show you how you will derive the linearized form. So in one model, you will get 1 over Q equals something something, and in another model, you need to do the linearization by a logarithm. So this is what you have on the second graph on the right bottom corner. So yes, I give you 5 minutes, so you guys do it by yourself, and then we start together.
Buset. Anjir, bisa gitu, cu.
All right, somebody already did the graph, and some people are finished. So let's try to solve it together. You unfortunately, I mean, if I would give you to share, I would need to cut this presentation, etc. But doesn't matter. I will share my solutions and you just double check and see if it's correct. And if not, then we can discuss and see what went wrong. So when you calculate, this is what you should get for adsorbent 1 and for adsorbent 2. This logarithmic value, this is all here a bulk phase, and this is the loading on adsorbent 1 and adsorbent 2. This logarithm value is coming from the linearization of the Freundlich isotherm, and this 1 over C value is coming, and also 1 over Q here is coming from the linearization of a Langmuir isotherm. Double check your values. If you do not have the same values currently, that is also okay. I will upload this presentation and you will have my solution, of course, as well, as always. And this is basically how it should look like. So this is the linearization of the Langmuir isotherm for adsorber 1 and adsorber 2. This is what why I said it's good if you have Excel before you, because you can just use the R-squared value to see how good is the fit. Of course, in the exam, we will not give you example like this where you would need a computer or anything to determine or to choose the adsorber. Most likely you will just have a process to determine the operating line and to calculate the throughput or something simplified. Or if we give you something like this to calculate or to linearize the isotherms, it would be, let's say, visually obvious that they fit or do they not fit. So if we have a look, we can say here that if we compare the R-square value, they are both larger for both adsorbers using the Freundlich isotherm. And as I said, from linearizing here, and if you go to display the equation also on your screen, you can directly see the slope and the cutout. The same also for Langmuir. So you can immediately read the K and N value in your Freundlich, or QM and K in your Langmuir isotherms. So basically, I will try to, I don't know, I will add it to my slide. What you have is for the Freundlich isotherm, you should end up with logarithm of the loading is equal the logarithm of K plus N times logarithm of the concentration. This is the Freundlich. And the Langmuir, now I don't have space here. For Langmuir, you should get 1 over your loading that is equal 1 over QM, which is this constant. Oops. Q, this is M, constant. Oops, guys, do you see a black screen? Or is it just... have no idea why my screen went black. Sorry. Yes, you can logarithm with any base. All right, we're back. Right, you're also back. You see my screen?
Yes.
I don't know why my computer refuses to write an M. I will put this in a printed letters. I just see that I don't have it on my slides, and this is only for you to double check if you've linearized it well. It's not gonna be this ugly, don't worry. Times 1 over C plus 1 over Q M. All right. So the upper one is the Freundlich. We do it with a logarithm, and the bottom one is the Langmuir. We simply linearize it in this way. All right.
Excuse me.
Yes.
Could you please explain how did you calculate 1 over q, like the previous slide? Could you please go back?
I will try to go to my previous slide. Sorry. It's not listening to me. Here,
Yeah.
you have it given. So you have C and Q. This is the equilibrium, this is the C, and this is the Q1, and this is the Q2. So you have all these values given in the task. Okay? And then you just put 1 over Q and 1 over C. All right.
I'm sorry.
Mhm.
I ask question as well. So how we know which ones are Langmuir, which ones Freundlich, or we just did it for both of them?
We did it for both. So this on the left is Langmuir, and so Langmuir you linearize in such way. You can only use logarithm to linearize exponential equations. For Langmuir, we had to do it in this way, right? And then you do
clear.
Yeah, and then you do it for both adsorbers. And then you get this. So the red ones is for adsorber 2 in both diagrams, and the blue one is for adsorber 1. And we see in this task, conveniently, the Freundlich isotherm has a bigger R² values for both adsorbers and works better for both.
Okay. I'm sorry. What's the R² values? How we calculate it?
If you have Excel before you, it's just the deviation from the linear fit.
Yeah.
Right?
Yeah, okay, I get it.
Know what I mean? Okay.
Thank you.
As I said in the exam, you're not expected to calculate any R² values or anything. This is just here for the convenience. In an exam, you will have more adapted values where you would either visually see, as I said, or not have to do it graphically like this at all, but have it in some different way. Maybe I give you just a linear equation to linearize it and determine the constants or something in a similar way, but not to do this. All right. And now what is left is to determine the final concentration and loading for both adsorbers. And as I said previously with the introduction to the task, we can determine, we always with adsorption work at equilibrium conditions, and we need to find a place where our operating line intercepts or touches our equilibrium line. And in this case, we have here, just a second. This here we would read the concentration and loading for the adsorber 2. So we would get around 0.06 grams per liter. And here we would read the loading for adsorber 2, which I would say would be around 4 point something grams per kilogram. For adsorber 1, we would have 0. Maybe we can say this 0.04 or so grams per liter in our solution, and we would have around 5 grams per kilogram loading. And this is our composition for adsorber 2. Which one would you choose for your process and why? Do you have any idea, suggestions?
Could you please again repeat the question?
So the question number 2 in our task is to determine the final concentration and loading for both adsorbents, which I just show you how to read from this graph. And also one of the questions under 1 is which adsorbent will be better for the above mentioned separation? Which one would you?
Adsorbent 1,
Mhm.
because for low concentrations we can get very high loading.
Yes, that's it. And also in this specific case with our operating line, we end up with a much more purified or much more removed from our solution, and we adsorb more. So yes, this is true. Adsorber 1, because we get more loading compared to what is in the solution, and with adsorber 2. That's true. All right. This is the last task for today, and also from adsorption. Do you have any questions?
Hello, can you hear me?
Yeah, I can hear you.
Yeah, could you please repeat what the operation line is and what we can read from the intersection? Operation
line is basically derived from the mass balance, and that's this. No. This. That's what I talked about at the beginning. So you have your adsorber, and based on what's in and what's out, you can set a mass balance and always get your operating line. This is very similar, I would say, maybe to extraction or something. At least the derivation of the operating line, and later this diagram. What was the question again? What is operating line and how did I read these values, right?
Yep.
So the adsorption is done at equilibrium conditions. So we need to wait for our adsorbate to adsorb on the adsorbent. That is why we are looking for an intercept between the equilibrium line and the operating line. Of course, as in every process, we can never go above the values that are set with the equilibrium, because equilibrium represents the maximum that we can achieve with our process. But adsorption is done at equilibrium. And when we take an intercept, or where the operating line that we before calculated and our equilibrium lines meet, we can read the compositions in our solution and on our adsorbent after our process. All right, and we read them at the intercept for adsorbent 1 and for adsorbent 2. Is this more clear? Yeah.
Perfect. Thank you.
All right. You're welcome. Any more questions to today's exercise?
Yeah. Hello.
Hi.
Yeah. Just wanted to the Q and the C values given in the question is slightly different, I think. I mean, like, have you plotted this graph using those C values, or?
Yes.
Like, so for example, in the question, it's yeah, the C value is like 0.2, 0.4, 0.6, 0.8, and 1.
Mhm.
While on the x-axis here it is 0.05. I mean, all the values are less than.
Yeah,
0.2.
so this is given for the larger range, you're right. But
So
no,
have you-
actually, no, this is for a smaller range. We have
Yeah.
all the way up to 1, and this is only until 0.2.
Yeah.
But
yeah.
this is just because the graph is zoomed in
Okay.
to
Okay.
this area so we can read.
Right. Okay. I just want to know if you use the same data points. Okay.
It's the same data, of course, yes. More questions?
Okay.
Yes, no? In the chat? No. All right, guys. Then I will finish up for today. If you think of any questions, write an email to me. If you want to do it in person, we can schedule a Zoom if it's in this year. If it's in the next year, then we can do it in person. Yes, so just feel free to write either with questions or with consultation requests. If you want to have, if you have several questions and you want to do consultations, please try to ask your classmates if they also need a consultation, so that I don't repeat the same thing several times, but also have you have one appointment for a few people. And yes, try to do this yourself. One more time, maybe some questions will arise as well. When it comes to an exam and everything related to an exam, and also if you have more questions first, when we finish all exercises, I will, of course, speak a bit more about the exam. I will send you an example of an exam so you can practice. I will we will organize one more appointment extra after we finish with these exercises, so that we can address all the questions that you have, either from the exercises or also if you had any problems solving this exam example that I will share with you. All right. That is all for today then. Does anybody have less time? Anybody has any questions for today?
I just have one quick one. It doesn't really matter what log we took, right? Like, because I think I took the ln and I think you might have taken log 10. It doesn't really matter which one, right?
It doesn't really matter, right?
Okay, gotcha. Thank you.
You're welcome. Yes. Any more? No. All right. Good. Then I think this is the last time we see each other in December, if I'm not mistaken, right? I think the next appointment we have on the 10th of January. Since, of course, some of you might see if we have a consultation or something, but if not, I wish you all great December and great holidays. And then I see you all, or most of you, in next year. Bye, everyone.
Thank you so much.
Thank
Bye.
you.
Yeah, thank you.
Thank you so much.
Cheers.
Thank you.
Thank you.
Thank you.
Thank you.
Bye bye.
Bye.